Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on calculating the error function. And in the previous lecture, we discussed how to calculate the error function for real numbers x, double numbers, and also complex numbers. And we looked at the different examples. This is one example that calculates the error function at the complex numbers whose imaginary part is constant j and the real part is changing, and we saw that we can accurately calculate it. But now I want to look at the whole family of error functions that we usually use in different applications. The first one is the inverse error function inverse, INV, and it's defined such that if y is the error function inverse of z, then error function of y is equal to z. So one way of implementing this, actually just for the real numbers double x, is to use a root finding mechanism, right? So basically, first of all, the domain of this is, or basically error function, the range of error function is between -1 to 1, right? So z, which is basically the domain of the inverse error function, is between -1 to 1. So if x is a real number and its absolute value is greater than 1, we return none, because that's not a valid number in the domain of the error function, right? The domain of the error function, this x should be between -1 and 1. All right. So what we do, we just create a root function which calculates the error function at t minus x. X is given, t is unknown, and we want to solve for this t such that the error function of t becomes equal to x. So what we're looking for the inverse error function of x, which has a value of t, and that specific value of t is satisfied when error function of t becomes x. So basically we solve this equation. So we have our root finder, which is a new real root, and we pass in our root function, and we use the Newton-Raphson iteration, which is pretty fast, and the initial value we give it 0, because we know that the range of x, the values of x, should be between -1 to 1. And so we give it an initial guess of 0. We limit it to 100 number of iterations. Okay, so this is one way, and obviously this is not the most efficient way. So inverse error function also has power series that we can use, but here for simplicity I'm just implementing it for real numbers double x, and I just use a root finder, right? The next one is the imaginary error function I, and that's defined based on the error function. So the imaginary error function I of z is -j error function of jz. And as you can see, we have already implemented the error function for complex numbers. So implementing this error function imaginary is very easy. However, we can improve its speed or performance when z is a real number, a double number, because then the input of the error function is pure imaginary. And then we can go back here and set x to 0 and calculate the error function at some jy. Y is a real number, so jy error function is evaluated at a purely imaginary complex number. So if x is 0, we already know that the error function of x is 0, so we don't need to calculate it because x is 0. And error function of -x squared is 1, so we don't care about it. We take care of this singularity here. And also in this series, again, error of e to the -x squared is 1, so we don't need to calculate it. And here x is 0, and the other nice thing is that when x is 0, this whole f sub k is 0, so we don't need to evaluate this part. Okay, and we only need to calculate the g sub k. X is 0, this term goes, k cosine is 1 because x is 0, k sine hyperbolic of ky. So I will implement this for just real numbers, so we can improve the performance of the evaluation of the error function imaginary when z is a real number, right? So we can do that, and I'll show you how to do it. The next one is the scaled complementary error function complementary. This x here in the name of the function means scaled. So error function complementary scaled is just a complementary error function times e to the z squared. So we have this exponential, all right? So it's exponentially scaled version of the error function complement. The next one is Faddeeva function, or wz, w of z. So wz e to the minus z squared, error function complement of minus jz, all right? Which is error function complement scale of minus jz. So here, if I set j to minus jz, e to the j squared, z squared is e to the minus z squared, right? Because j squared is minus 1. So Faddeeva and the scaled complementary error function is pretty much related, and here's the implementation. Public complex, it must return a complex. Faddeeva by taking a complex or real value or complex value, and we're calculating the exponential of minus z squared as a complex number times error function complement of minus jz, all right? And remember, error function complement is just 1 minus error function, right? And but the scale is not true, so error function complement scaled. We can define a scaled error function with e to the z squared times the error function, and then the sum of the complementary scaled and the error function scale is e to the z squared, right? And w of z is another notation for Faddeeva, right? And I believe SciPy uses w of z for Faddeeva. The other one is dawson function, d of z, which is square root of pi over 2 e to the minus z squared, error function imaginary of z. And as you can see, if z is a real number, a double value, then error function imaginary is real, and therefore the dawson is also real. And the other thing is the derivatives and integrals of error function. I mean, the nice thing about error function is that its derivatives and integrals have closed form expressions. d dz of the error function of z is just 2 over square root of pi e to the minus z squared. And that's no surprise, because we define the error function based on the integral of this function 1 over square root of pi, and it's an even function, so I can write it 2 integral from 0 of x of this, and then d dx is 2 times 1 over square root of pi e to the minus x squared. And that's how we are writing down this derivative. Now for the integration, we use integration by part. So integral of error function dz is error function times z minus integral of z times the derivative of the error function, which is 2 over square root of pi e to the minus z squared. But then z e to the minus z squared, integral of this has a closed form expression, which is 1 over pi e to the minus z squared, right? So here I'm using the function interface in java.lang. So it's a standard Java library function double error function deriv. So x goes to 2 over square root of pi exponential of minus x squared, and another functional interface for error function integral. X goes to x error function x plus exponential of minus x squared over square root of pi. Now we can overload this with another parameter, which determines the constant of the integration, all right? So let's head to Eclipse. Here I have my error function, and I have this integral. So I have a version of double x, and basically, actually we don't need this x. So this integral just calculates the integral of the error function from a, x equals a, to x equals b. And I have this error function as a functional interface, and I can have another function that overrides this with this double c. and this c is the constant of the integration. All right, so this c is just the constant of the integration. So for the error function imaginary, so for the double and the complex, as you can see, I have just used the definition of the error function for complex, but we can actually improve this. So let's highlight, comment this, and then we go here, and what we already know is that if basically z is a double number, then basically the error function imaginary x is 0, right? So x is 0, because remember, error function complex, error function imaginary of 0 of z is just minus j error function of, let's go back to the PowerPoint, error function of jz, error function of jz, right? So if z is a real number like x, so we are calculating at, or let's say y, jy, so y was the imaginary part, so basically we can just call this y, and y is the imaginary part as it should be, and then this coefficient is just 1 over pi, all right, e to the minus x squared, and term 1 is 0. We don't need to calculate this because x is 0, all right. And when x is 0, term 2, this sinc becomes 1. We don't need to calculate it. This sine becomes 0, and this cosine becomes 1. All right. And then we have the real sequence, which calculates to 0. This sine is 0. This x is 0. So this calculates to 0. We don't need to calculate it. And then sine of x times x for the imaginary, this sinh and this cosine evaluates to 1. And then real sum, we don't need to calculate this. Imaginary sum, this x is 0. And then okay, we don't need to calculate the real sum. And then coef, this term 2 has a j, so there is a j here and there is a j here. So term 1 is 0, so we can factor that j out. Okay, and then we can declare these as double. And we're not using this term 1 because it's already 0. Okay, so as you can see, we were able to simplify it, and obviously we can go and test it. So in this test error function class, what I have, test 1 is what we looked at. Test 2 is basically calculating the error function at some different error functions, the error function at 2j, and then error function imaginary and error function complementary. So let's run test 2 here. Okay, so I'm going to so we are calculating the error function. We can just put this here. So error function of 2j and is 18.5648. So let's fire up our Mathematica. Error function of 2I point, it's 18.5648 times I. All right, and their error function imaginary of 2 is 18.5648. Now, as you can see, we have an I here, so let's go back here. Let's see, if if x is 0, then we get a, okay, so error function. So this was for calculating the error function of jy, and if we multiply it by minus j times j is minus j squared, which is 1. So we don't need to actually multiply by j. All right. And then the problem here is that the return type should be double, not complex. Okay. So for real values, error function imaginary, it's actually a real number. So the name is a little bit misleading, but if z is real, the error function imaginary is a real number. All right. So let's look at the Mathematica, show all digits. The error function imaginary gives the imaginary error function, and it's 18.5648 02414575556. So we have about 15 decimal places of accuracy compared to Mathematica. And then we have error function complement of 2 plus I, which gives us minus 0.0036 plus I 0.0113, which is 112.9. All right, 259. So all the implementation work fine for a complex numbers. So in test 3, I'm just plotting the error function. So let's look at it one more time. In test 3, I'm plotting the error function from minus 10 to 10, and we know that the error function, the range is from minus 1 to 1, as you can see, and the main variation happens between minus 3 to 3. Outside this region, the error function is basically 1. Okay, so in test 4, I'm plotting the error function for x plus j. X is a real number. And you see the real and imaginary parts. In test 5, these are other tests that we can look at later. And let me see if I have the, okay, so error function imaginary, let's plot it. Plot it. So test 14, and in test 14, what I'm going to do, public static void test 14, I'm going to create my error function, func new error function. All right. And then we're going to create our variable x, Matthew Tears, lean space, -5 to 5, 1000. And then I'm going to plot the imaginary error function. Double error function I is array func. Apply, t goes to func.error func imaginary for t. And then we're going to apply it to x, and now we create our MATLAB figure, MATLAB chart fig, new MATLAB chart, fig.plot x error function imaginary, fig.render plot, fig.show with the exit flag. All right, so test 14, and this is our imaginary error function, And as you can see, it goes up very fast. So let's limit it to -1 to 1. Okay. So from -1 to 1, let's export it to Python. Let's call this test. Open it in a text editor. Copy them to our Jupyter notebook. Okay. And so x0, y0 is the imaginary error function. In the SciPy special, I believe we have the error function imaginary of x0. Let's see. Okay. As you can see, we get a perfect fit. So this is a whole family of the error functions. And again, I implemented the derivative and the integral as functional interface. So they return functions, and then we can use those functions to evaluate at any point, right? So it's not limited to any input variable. We can evaluate them at any x because they are a function, they are an interface, all right? So I hope you enjoyed this lecture. Please stay tuned, and I'll see you in the next one.